Namaste, this is Manor P. Hiremat from SVC College, studying in EC department. I'm here to present problems based on Thevenins equivalent circuit and superposition theorem. So before going to the problems, let's understand what is Thevenins equivalent circuit and superposition theorem. Thevenins equivalent circuit. The equivalent circuit is a voltage source with a voltage VTH in series with the resistance RTH. The Thevenin equivalent voltage VTH is the open circuit voltage at the output terminals of the original circuit. Superposition theorem. Superposition theorem states that in any linear bilateral network where more than one source is present, the response across any element in the circuit is the sum of the responses obtained from each source considered separately. In contrast, all other sources are replaced by their internal resistance. Means that the Thevenin's theorem also states that an equivalent circuit can replace any linear circuit consisting of various resistances and voltage with the single source voltage and a series resistance connected across the load terminal. So these are the two questions to be discussed. The first one is based on Thevenin's equivalent circuit, and the second one is based on superposition theorem. So the first question based on Thevenin's circuit goes like this. The Wheatstone bridge in the circuit shown in figure 0.1 is based when R2 is equals to 1200 ohm. If the galvanometer has resistance of 30 ohm, how much current will be detected by it when the bridge is unbalanced by setting R2 equals 1204 ohm? So the circuit goes with first comes the 1200 ohm, that is of R2. It consists of four resistors. R1 goes with 900 ohm, R2 is of 1200 ohm, R3 is of 600 ohm, and R4 equals 800 ohm. And it also consists of 120 volts. And the galvanometer is connected as the bridge circuit between A and B. So the solution to find VOC, first we have to remove galvanometer current from the circuit connected between A and B. So later, after removing the galvanometer from the circuit connected between A and B, we have to find the voltage at the particular point where the galvanometer is removed from the points A and B. So there are three loops in the circuit. The first loop is assume first loop as I1, and the second loop as I2, and the third loop as I3. So first let's consider I1 and I2. So these are calculated as like this. I1 is equals to 120 by 900 plus 600. 120 is of that in the circuit, 120 volts, and 900 plus 600 it is added due to the resistors are connected in series. So 120 by 900 plus 600 is equals to 120 by 1500 ampere. I2 is equals to 120 by 1204 plus 800. So as we come to the second loop, I2, the resistors are connected in series. So the 1204 and plus 800 is added, and also it is divided by 120 volts. So we get the answer as 120 by 2004 ampere. So applying KVL clockwise along the path 1204 ohm, 1204 ohm, V B minus A 900 ohm. We get 1204 I2 minus VT minus 900 I1 equals 0. So simplify the equation and we get VT equals 1204 I2 minus 900 I1. Later, we get 1204 into 120 by 2004 minus 900 into 120 by 1500. So the answer is 95.8 95.8, 95, 95.8 millivolts. So the next slide. Now to find the resistance across the RTH, deactivate all the independent sources and look into the terminals A minus B to determine the Thevenin's resistance as shown in figure 1.b. Before that, first sort the circuit in the loop 1, I1. After sorting the circuits, we get RTH equals RAB plus 600 parallel to 900 plus 800 ohm parallel to 1204. So as we sort the circuits at the loop 1, and we need to determine the resistance across the point A and B. So the resistors are in parallel to 900 parallel to 600 ohm and 1204 ohm parallel to 800 ohm. So we get 900 into 600 by 1500 plus 1204 into 800 by 2400. So the answer is 840.64 ohm. Hence, the Thevenin's equivalent circuit consists of the 95.8 millivolts source in series with 840.64 ohm resistor. If we connect 30 ohm resistor galvanometer resistance to this equivalent network, we obtain the circuit in figure 1.c. So observe in the figure, we have to find the current on the Ig. So Ig equals 95.8 into 10 power minus 3 divided by 840.64 plus 30 ohm is equals to 110.03 microampere. So now let's move on to the second problem that is based on superposition theorem. The question goes on like this. For the network shown in figure point 2, apply superposition theorem and find current I. So we have to find current I over in this question. So it consists of two resistors. One is of 8 ohm and one is of 4 ohm and 5 ampere, and the load is of 10 ohm. The, the solution goes on like this. Open the 5A current source and retain the voltage source. So the resulting network is as shown in the figure point 2A. Observe the figure. The impedance as seen from the voltage source is Z equals 4 minus J2 plus 8 plus J10 into minus J2 divided by 8 plus J8. So that equals to 6.01 angle of minus 45 degree ohm. Hence, we have to find the current I. So as we observed in the figure, IA is equals to J20 by Z is equals to 3.328 angle of 135 degree ampere. So next, sort the voltage source and retain the current source. The resulting network is as shown in figure 2.b. So here I3 equals 5 ampere. Applying KVL for mesh 1 and mesh 2, we get 8I1 plus I1 minus 5 into J10 plus I1 minus I2 of minus J2 is equals to 0. And the resulting solution is I2 minus I1 into minus J2 plus I2 minus 5 into minus J2 plus 4I2 equals 0. Simplifying, we get 8 plus J8 I1 plus J2 I2 is equals to J50. J2 I1 plus 4 minus J4 I2 is equals to minus J10. So this is the three loops I1, I2 and I3. So by solving those two equations, we get IB is equals to I2, which is of 8 plus J8, J2, J50 minus J10 whole divided by 8 plus J8 into J2 divided by J2 4 minus J4. So that equals to 2.897 angle of minus 23.96 degree ampere. Since I and IB are following opposite direction, we get I equals IA minus IB, 6.1121 angle of 114.78 degree ampere. So that was our main answer. And I thank you for watching full video, and please support me. Thank you.